Good to see you all here this morning. It's wonderful to be here. I've come in from Western Canada. It's a long flight, but it's my first time in Malaga, and it's a lovely place here, so thanks for having me. I want to tell you about Local First software. So Local First software is a track of research that's come out of our research lab, Ink and Switch. We're an industrial research group exploring tools for thought. When I say industrial research, I mean that there won't be any math equations on my slides. And when I say research, I mean that I don't have any product that I'm here to sell you. And let's talk about what I mean by tools for thought, though. So this man is John Conway. If you've heard of Conway's Game of Life, he was a mathematician. He did a lot of interesting theory work. And this is his office. So there are lots of tools for thought happening in here. I think you could argue that the computer is a tool for thought or can be used as a tool for thought. He has lots of physical manifestations of thinking, and he has a very messy desk covered in papers and other physical objects. So when we talk about tools for thought at Ink and Switch, we mean not just sort of the technical manifestations of how to make computers better for thinking. We feel that in many ways, computers have become much worse for thinking in recent years. But also, we try to take a very broad frame on the problem and think about all the possible contexts where you might need to think. So let's look a little closer. What are the properties of good tools for thought? Like with a good chef's knife, the tools that we use to think, a pen and paper is a great tool for thought. A chef's knife is an excellent example of a responsive tool. Okay? Our most used tools should feel the best in our hands. They become an extension of our body. They behave predictably. Because if they're slow or they don't behave how we expect, that degrades our ability to work. We want our tools to serve us immediately. One thing we find when we look closely at creative pursuits, and by creativity, I don't mean solely artistic creativity, but any kind of creative endeavor, whether it's scientific publication or journalism, or just making plans at home or with your friends. It often involves collaboration and paradoxically privacy. So if you think back to sort of the pre-cloud world of collaboration, the way you'd write a document and you'd email it to someone and then, oh, this is the document version 2 because you downloaded it twice, and then you put final on it and you send it back, and then you realize that you forgot something, so you put final on it and it comes back again. And there was this terrible kind of management problem of figuring out where your data was. When we moved into the cloud, data went from being a thing to being a place. And so this has a lot of benefits. You can access the same Google Doc from anywhere in the world on any device. But all of a sudden now you've lost this ability to work in private. And this is something we heard over and over again from people who do creative work, which is that it's kind of uncomfortable when you feel like someone's peering over your shoulder as you're working. As a programmer, you don't really want everybody else on your team to be subject to the middle of a patch. It'd be impossible to get anything done without the ability to check out a repo, work on it, and then put up a PR when you're ready. Another property that is really challenging to get in the modern computing world is longevity of software. Often when we talk to creative people, we hear about creative projects that can last not just months, but years or even decades. Here on the side is an image of WordStar, I believe, 4. This is a text editor. This is the text editor that George Martin is using to write the Game of Thrones novels. And he's using it because when he started the series, this is what his computer was. And so he continues to work in that. If you use SaaS software in your long-running creative endeavors, you really have to hope that they don't, go on an incredible journey when they get acquired or shut down. You have to hope that they don't, pivot and change the product in a way that makes it no longer suitable for you. You have no ownership, you have no agency over that process. And if they do shut down, we're still, you may only get a handful of JSON as compensation for your time. Relatedly, creative endeavors happen in a lot of different places. And this is maybe just another riff on the same theme of a tool being responsive and predictable and having longevity. But it's really upsetting when you are looking at something on your phone and you kind of walk into another part of the workshop and the Wi-Fi is blocked there because there's some heavy tools in there, or you're going someplace and you have the GitHub issues open and the Git repo checked out. You open up your laptop to do some work, and then instead of seeing the GitHub issue to remind yourself what you were going to do, all you see is that stupid dinosaur game, right? It was there on your machine, but it's disappeared. And these things can really disrupt people's ability to work, and they can sap our creative energies. To do creative work requires actually sort of an unusual state of affairs. You need to be able to get into a state of flow, to focus, to do deep, important, meaningful work. And so to summarize all this, we feel that software tools should be always available, everywhere, anytime. They should be collaborative, but also support privacy. And we want them to be really responsive. We want good performance. We want them to feel good in the hand, so to speak. So let's talk a little bit about how, this was sort of the motivation that led us towards developing these local first ideas. We think they may be more broadly applicable than just this tools for thought space, but let's look a little bit about how we can go about building them. We're going to take a 3-point strategy. Okay, we're going to move the compute into the device. We're going to write our software in a way where it runs on our computers or in our hands and our phones. We're going to have an authoritative copy of the data locally on our device. And then we're going to use the cloud and the internet to augment the capabilities of that software. We're not saying we don't want the cloud. We need the cloud, but we don't want to be reliant on it for normal operation. So practically speaking, you could do this in a lot of ways. If you're building mobile apps, you could use Swift or Kotlin. But in our research, what we generally do, though not universally, is we run things in the browser. We've been building PWAs, that's progressive web apps, to ensure offline function. We store data in local storage or with the new file system access API in the browser. And we use something called a CRDT that we've been working on in partnership with Martin Kleppmann at the University of Cambridge called AutoMerge. And that's a really key piece of the technology. We'll do a little live coding on that later. And then we have extremely simple cloud services. It basically just like a WebSocket echo server. We all connect, and any message that goes to it goes to everybody else. It's a little more complicated than that, but not much. So we've been doing this for about 5 years. We started with very kind of rudimentary things, and we've been sort of moving along. So let's take a little look at some of the prototypes of things we built. This was our very first experiment. It was called Trellis. It was a Trello clone. We have kind of a few interesting things going on here. One neat property I'm going to point out is that if you look, there's sort of the Trello cards on the left. On the right, you have all of the changes that have happened. That's an event log. And so what we're actually doing here is we're instrumenting the document on the left and automatically generating the history of it on the right. We did some really crazy things. This was one of our first projects. We were trying to do all the collaboration over peer-to-peer connections using WebRTC in the browser. WebRTC needs something called a signaling server. You can make a peer-to-peer connection once you find the other person, but it needs a server that you rendezvous at to discover each other. But we didn't want to have servers, so we were really trying to push the bounds on this. My favorite weird experiment that you could only get away with at a research lab was that we gave everybody a Slack API key for their client. So everybody's client became like a bot that logged into a special Slack channel, and the apps would just chat over this channel with each other to discover each other and then do WebRTC handshaking right there in the Slack room. It worked pretty well, except if you had 5 or more people online, it would start to overrun the Slack flood control, and then it would just sort of decohere and fall apart. But this worked. This was incredibly slow. We had n-cubed performance problems in the CRDT, and it was very rudimentary. But it was promising enough that we kept going. Our next prototype here is Pixel Pusher. This is a pixel art editor. And the real goal here was, okay, well, we'd done it once, but we wanted to try using somebody else's code and make sure we weren't cheating too much by sort of picking a problem that we had control over. And this was a really fun one to play with, but it was the first time we started to explore kind of what does it look like to have branching and merging, almost version control over your pixel art. And so you can see some sort of evidence of that on the side. In addition to being just like a fun domain, this was the first time we experimented with building against DAT and IPFS, which are peer-to-peer data synchronization technologies. We'll come back to them both later, but we eliminated IPFS from contention at the time because IPFS is built on a model of content-addressed hashing. So the idea is that the file name is the contents in a certain sense. And that meant that every time anyone changed a pixel, you had to somehow get the new name to everybody. Now, IPFS these days has some more capabilities. Maybe I would end up somewhere different, but we ended up using DAT, or now called HyperCore, to do a lot of work. From there, we got much more ambitious. This is, we call this like cards on a canvas or a spatial canvas app. And this is a multimedia thing. We were using all kinds of different files. You could share by giving a link to someone and they could paste it in and open the app and it would spider down and pull all the data. This was really fun and it gave us a chance to really kind of like push on the bounds of how this works. And so everything you see on this screen here is a CRDT with another CRDT inside of it. So the root of the document that we're looking at is one big CRDT with like a user avatar for me in the top left corner, and then another CRDT with the positions of all these cards, and then the text cards are each their own CRDTs as well. This is where the DAT model started to break down. Each of the cards and elements had its own URL and name, and what happened was we just got to this place where we were trying to synchronize literally thousands or tens of thousands of CRDTs at once. And each one of those had its own file for each author. So we were like crashing Airbnb networks with like too much network traffic, and we were like running out of file handles and blowing up OS X. So this is the fun of research, is you get to run into these weird corners. That led us into Cambria, which I wish we had more time to talk about, but let me see if this video is going to play. With Cambria, we were trying to solve the problem that on the left, we have sort of an imagined version control here. And on the left, you see there's like an issue clean fossils there with a tick box next to it for whether that's been done. On the right, you can see 3 states, to do, doing, and done. And what we found was that as we were building this software, we would add new features, but people running the old version of the software wouldn't have them yet. But because we have this live real-time collaboration, we were getting crazy corruption problems where people were writing simultaneously different formats of data into the same document. So Cambria was an attempt to rationalize that by using something called lenses. And so you can see here that as the document changes state on the right from the more complicated app, it actually is changing the left one, which has a simpler data model. So we created bidirectional mappings that you could compose. And this graph here shows how even if you have many different versions apart, as long as we can find a path through this sort of translation layer, we can connect arbitrarily and in real time any versions of software. Now it's playing again. We spent some time thinking about identity. This is Backchannel. It was a chat application with no account names that uses pet names and Pake to create secure communication and prevent impersonation. Then we did Paratext. This is our rich text CRDT. Turns out that people like to have formatting in their documents. And then lately, this is unpublished. This is Upwelling. We're just wrapping this project right now. And this is an editor built on top of that rich text work where we've been trying to explore this kind of like, how can we hybridize what developers have on the one end, which is this sort of deliberate process of pull requests and collaboration, with what authors in Google Docs have at the other end, which is sort of track changes and commenting and in-place review. So I'll try and show that if we have time. So it's a lot that we've done. It's been a busy time. So I'm going to try and summarize some of what we've learned. This is a US aircraft carrier. It's the Nimitz. The crew is 5,000 people, and it cost about $8.5 billion US. I'm showing you this because I'm going to overlay the Cloud Native Foundation's landscape map at 1-to-1 size on top of it. We have been building aircraft carriers in our industry. We add more and more complexity. This is sort of the theme of the keynote, which is we keep building more and more layers with more and more tools to manage the layers below them, and then new solutions on top of that to go below it. And what we want, in many cases, is not this. What we want is a bicycle, right? A bicycle is something that's intimate, it's personal, it has a crew of one. It costs quite a bit less than an aircraft carrier, but it doesn't do the same thing. So I'm not here to tell you, oh, you should only be building bicycles. But I'm telling you that a lot of the time we're using the techniques to build aircraft carriers when what we really need is a bicycle, something simple, something personal, something that can take you where you need to go and that responds to you alone, and is a heck of a lot easier to maintain and operate. What we found, we came to this local first software concept from this domain problem. We wanted to have these kinds of software properties, and so we started figuring out how to build software that way. What we discovered is that it's weirdly charismatic. There's something really amazing about it works on my machine is the answer. It's like the Docker joke, oh, it works on my machine, well, we'll ship your machine then, right? But you do with local first software. You're kind of there. You don't have to push anywhere. You can just use it. There's nothing that's going to page you at 3 in the morning because the software is running on your computer or on your users' computers. There's no Amazon bill to pay. There's no user data to secure and then worry about GDPR compliance or getting owned. It's a really great feeling if you're in a place where you can use it. And I think many of us actually have more opportunity to do this than we realize. It's about kind of rethinking our relationship to the cloud. If I close the lid on this laptop and the software is only running here, obviously it disappears, and that's kind of a pain if then I want to look at it on my phone as well. So I'm not suggesting that we don't want to have our data in the cloud or to be able to reach it from other places. What I'm saying is that we want to change the relationship from one where the program runs in the cloud and we can look at it when we're online, to one where the program runs in our hands and where we can send the data for durability or accessibility to the cloud. We can take advantage of the powers of the cloud without being totally dependent on it all the time. A few other notes. One thing that has been an ongoing kind of challenge for us is the real ultimate vision of this is that my laptop should be able to talk to your laptop right here in this room without going to Ashburn, Virginia to the AWS data center. And a lot of the time that's what's happening, right? You want to work with a coworker on a piece of software, you're in the same room, sitting at the same table, looking at screens side by side. Any communication between those computers is actually happening going across the ocean to some data center, to some other server, and then coming back to you. One, that's crazy, but two, it's also very slow and expensive, and it doesn't need to be that way. So although ideally peer-to-peer networking would be kind of the answer here, practically speaking, you can't. And I know there are maybe some people from Cisco, I don't know if anyone is in the audience, but this is a problem only you can solve. We can't solve it. Yeah. Well, so the problem is, and we don't have time to talk about this today, but the way that we actually talk across IPv4 networks is that we don't actually talk directly computer to computer anymore. We go through our routers, which talk to each other and forward the traffic. And this process is called hole punching when it's done in sort of an ad hoc way. And if you want to have local communication with two laptops side by side, you need to punch a hole out of your router and then immediately come back through, and that's called a hairpin. This doesn't work except in places where users have infrastructure control. So the places where you want this feature most, like at the library, the cafe, or in an office, are the places where it works the worst. And that was really frustrating because we had these great experiences where, when our distributed team was trying to collaborate between Berlin and San Francisco, works great. Get together in the Airbnb, doesn't work at all. Spend your whole time together trying to figure that out and not get any work done. There are other options. You can explore Bluetooth Low Energy. There's some new local Wi-Fi solutions, but a lot of it's kind of poorly documented. And honestly, after years of trying, I'm kind of frustrated. So by all means, if this motivates you, I would love to see your solutions. I also want to make one other note, which is that in the case of WebRTC, I've seen so many projects do this. They're it's peer-to-peer. You just connect to the signaling server and then the things talk. That's not really peer-to-peer because you've got a server. If you've already got a server and you're just embracing the fact that you're going to need to have a server online to communicate, my advice is really don't mess around with peer-to-peer stuff. Just use that server because, man, this stuff is really fragile and very hard to debug and full of weird corner cases. So, don't Don't spend all your time there unless that's a problem you really want to solve. Just set up a simple relay server. It's fine. One of the interesting things about working on this software is that I've come to view offline as just having very high latency. And so what happens is we call this the continuum of trouble across the bottom here, and it's how users perceive latency and the consequences of it. So if you and I are typing in a document together and we are, say, somewhere below 300 milliseconds of latency, we perceive that as instantaneous as users. And if there are conflicts, we don't notice, right? I can't tell that we, as far as I can tell, we did the same thing at the same time, so it's arbitrary which one happened. So if something goes weird because there's a conflict, it's perceived as user error. Sort of going up a few orders of magnitude on the time scale, we get into sort of the time that web requests take. Let's say 300 milliseconds to 30 seconds, and yes, you should be optimizing your page request times. But conflicts here happen at the document level, and when they happen, what we've observed is that rather than trying to figure out what went wrong, people just rework. They go, oh, that's weird, and then they just fix the error manually. They don't pull out a tool. Past sort of like 30 seconds of divergence, and again, these are all sort of soft boundaries, you get into harder problems and more frustrating things. And as we all know from dealing with like a complex three-way Git merge, it can sometimes be as much work to resolve the conflict as it was to write the patch. This is where manual interventions that are trying to preserve the original document become more common. And this is where you need tooling. But if you are trying to build offline modes, the takeaway for this is if you're building offline modes for your software, you're going to have to build version control for your software, because if your users can go offline and you don't want to throw their data away, past a certain time threshold, there's just enough time for weird stuff to accumulate that you're going to have to give them tools to solve those problems. In general, I'd like to encourage you, whether you're building local first software or not, to move away from the fragile sort of instinct to use API calls to manage change in your application and towards using data synchronization. When you make an API call, anything can happen and nothing else can happen until that call actually completes. Rather than sending an API call, which assumes that you're online, that you have a strong connection and that you'll hear back, and also anything can happen, right? Like from the client side to the server side, I ask it to do something, who knows what happens, right? Like ideally it does what I ask for and I get the response. But if you're doing like sort of optimistic local updates, but then the server has changed, you can start to get like decoherence, right? Where everybody sees something different. So rather than doing that, if you write your data locally into some kind of store and then synchronize that, whether you're using like RealmDB, which is something that Mongo does, or a CRDT like we do, as a strategy, this is a much more robust solution, and it's one that supports offline modes or local first modes much better. It's also just easier to reason about as a developer, right? You can look at the data that you have, you can see how it's changed, and you can see whether things are in sync. So it's a very robust solution. And they call it a browser, not a keeper. So the world that we live in is one where most of our software is now being run out of what used to be a glorified PDF reader, right? The web was not originally a dynamic application hosting platform. It was a place to put your academic, CV online and like link some advice about how to operate the coffee machine at CERN. So because of that, browsers aren't really good at storing data. They're certainly not good at storing the authoritative copy of data. And over the years, the browser has always been struggling at the edges of becoming a real application platform. That's why we have so many Electron apps, right? It's just like, it's not quite there. So my advice is if you're going to explore this stuff, we've built a bunch of Electron apps and then tried to port them back to the web, and that's terrible because you get addicted to like node libraries that don't work in the browser and binary dependencies. My suggestion and encouragement to you would be to start by building a PWA, but PWAs actually are really kind of gross to use as standalone web applications. I know Google keeps trying, but it's just not there. So my advice would be build a PWA, you can share it with people via a link, and then wrap it in an Electron app for distribution. There's something really nice about downloading and installing software. You really can trust that it's there. All right, is anybody interested in the live demo? Yeah. All right, let's Let's see what we can do. This is always the part of the talk where things get dicey. How am I doing for time? Okay, I've got lots of time. So first, I'm just going to show this. This is Upwelling. This is an intentional text editor we've been working at. No one's ever seen this outside the lab before, so I wanted to give you a little sneak peek at some of the work we've been doing. Here we've got a little document that I made, and I can click through and we can see, these are kind of like branches. These are edits. So I could click over here and say, oh yeah, I didn't have the accent on Malaga, so someone made a comment and said they corrected the spelling, and then maybe I come over here, there's a different branch that has a bunch of edits. We can't really see what's happening, so we're gonna turn on show changes. And now we can see, because every edit is made with attribution by a CRDT, it's not like someone decided in advance to track changes. This is essentially like a git diff view on the rich text underlying. And I want to say that I was going to say that we get this for free, but actually we built all the capabilities to do this as part of this project, so it was very difficult and expensive. But it'll be for free in all the other projects now that we've built it. And so it's really cool to be able to do that. And I can actually merge this change into the document, and then this is the joy of research. Great. Let's see if okay, it came back. Oh, live demos. Merge. Okay, so now I've merged this one. So now I can go back to this other branch here, and you can see now this one is floating on top of the underlying demo. So this branch has automatically been pulled up to sit on top of the things I've just merged. And so we have this ability to work like developers do. That you could think of this as like an automatic rebase. But so now we have this ability to build these documents intentionally. Not only that, but I could click in here and I can go back and see all the different changes highlighted by versions. So if I was like the lead author on a scientific paper, I can see what's changed from layer to layer, from patch to patch, and who made the edits when. And you can't really do this with Google Docs. You can go back and see how the document was, but you can't really see what's happened like we can with software. So we're pretty excited about this. It's hopefully this will, we'll see how long it takes to write the paper, but I wanted to give everybody a little taste of that. Now, okay, this is where we get to the live coding. I talked a lot about CRDTs and applications, so we are going to build the world's least exciting to-do app together here on stage. I'm going to start by showing you the whole source code. This is what we have so far, okay? It's literally just an H2, a UL, and a form. That's the whole thing. And then we've imported AutoMerge and this local storage wrapper. So let's look at the program. We're going to make a document with this AutoMerge in it. Is that big enough for everybody? At the back, bigger? Bigger, always bigger. Okay, so I have a server running here. It's just a file server because you can't load ESM modules out of file URLs. So it's going to be out of port 8080, but it's just serving the files up. So we're going to initialize the document, and here's our schema. It's not written in TypeScript, but I wrote the data document format here as TypeScript. So we just have a document which is an array of to-do items. Every to-do item has a text and a done field as a Boolean. So we have a function here that says add item, right? And when you push enter in the form, it's going to add an item. And we have another function called toggle item, and if you click on the thing, it's going to call this. This is the magic part here. So this automerge.change, we pass that document we created in, and then if there's no items array yet, it makes one. And then we just push the object into that array. Now, the reason we have this change function here is we are taking the document and we're putting a wrapper around it with the JavaScript proxy object. So any changes, you can't change the document outside of a block, and inside of this block, any changes that you make are instrumented. And we will see that you called push on this array, and we'll record that so that when it's replayed later, we can see that. And we'll look at this actually running in the browser. We'll take a look at what those operations look like. And then that just returns a new version of the document, and then we call update doc, which will just re-render the document. So this is our, I didn't want to get into a holy war about React versus Vue versus Svelte, so here's our render function. This is like real low fidelity, create element, list item, inner text, is, this is React from the Stone Age. So you got the idea. So okay, let's look at that for a sec. It is the world's least exciting to-do app. Okay, so here we go. Let's have a conference. Cool, great. And you can see here the operations that are happening. Let's pop one open. So we've got some object ID here, and then we are setting it to false. Cool, on done. All right, so now we refresh, and oops, all our data's gone. We should probably be storing this somewhere. Fortunately, I have written a robust and complicated persistence function here. It's this 10 lines or so. So what we're going to do is we're going to literally just call automerge.save, which gives us a binary blob for the document. And then we're just going to shove that in local storage under a document ID. And when we open the window, we're just going to load it. Does that make sense? I can go through this in more detail, but I'm hoping that's sufficiently simple that I will bore you if I do more. So okay, we're going to save that. I'm going to hold Shift when I refresh. Great. There we go. Okay, so hold on. There's one other edit I needed to make here. So yeah, I gave myself a to-do, which was remember to add save to the update doc. That goes right here, because otherwise it's not going to save. Cool. All right, so refresh. Oh, I needed to pass new doc in, didn't I? Thanks. Okay, and this is now the world's second least exciting to-do app. Okay, good. So add storage, add collaboration, check. Okay, so now if we refresh, nothing happens because it's there. So then we can, let's make a new browser window, we'll paste it in. Ooh, but we didn't actually do what I wanted to do here because I just loaded it out of local storage and it's at the same origin. So we haven't done anything yet. It'd be much cooler if we were actually collaborating. So let's do that. So we're going to go in here. We're going to grab my extremely robust network code. Chrome has something called a broadcast channel. Do people know what the broadcast channel is? Okay, a broadcast channel is just a message bus that's available across all tabs for the same origin. So I can just put a message in that, and any other tab running off the same web page will see what I put in there. So we're going to write a sync function which says, hey, what changes have happened since the last time we called sync? And then we post that as a message. And then everywhere else we'll say, hey, we got a message. Let's apply those changes locally, and then render the doc again. So let's copy that out. And then normally you would just call this every time, but I'm going to do it manually with a button that we append just so that we can see the effect slowed down a little bit. So we'll just paste that at the bottom here. Save. Oh, hold on. This is now the third least exciting to-do app. Okay, cool. So let's stick that one there. Let's stick this one here. I also need to reload that one or I won't be listening. Okay, so we add collaboration and finish talk on time. That's for the hosts. All right, so now if I hit transmit changes, hey! I really wasn't sure that was going to work. All right, cool. So we could spend more time on this. It's bidirectional. One of the really neat things about this is that it uses a synchronization protocol under the hood. Like these changes are incremental. So if we had a really big document and we make a change, it only sends what's delta, right? It doesn't send the whole document every time. So this can actually make your networking protocols much more efficient than they are. Okay, so that's the end of the live demo. I'm gonna wrap things up for you here. The first sort of concluding observation I want to make is that developers are already used to local first software, okay? You don't, at least I don't, want to live in a world where I have to work on software like I do a Google Doc, where I can't do it on my own, where I have to use the same IDE as everybody else and where everybody else is watching me work. I want to check out the Git repo. I'm going to use my IDE with my keyboard shortcuts and my plugins and things set up. And when I'm ready to share my work, I'm going to push it. Why don't we have that for anything else? It's actually kind of weird when you slow down and think about how good we have it as developers compared to everybody else. But it's not perfect, right? We've got a lot of GitHub PRs are great. but they're kind of complicated and the UI is bad. So, by showing you all of these ideas and this new technology with the CRDTs and lenses for real-time translation of data and all of this kind of research prototype, I know that I am proposing ideas that are radically different than how we're all used to working. I was one of the original staff at Heroku, the platform as a service. I have written a lot of 3-tier, Postgres, Heroku dynos, front-end app style applications. And I've written plenty of, larger scaled out back-end infrastructure and things that use 25 Amazon services where you have a 7-figure AWS bill every month. And, I've been there, I've lived in that world. And I wanted to just plant a seed with all of you to imagine that actually maybe there's a way to do things differently. Maybe we don't have to just build these aircraft carriers when we want to go around the block. And in fact, because we're so used to thinking about aircraft carriers, we can only go to the places that that kind of design takes us. When we build software in this other way, when we think about software in this other way, we can make different kinds of things. We can go different kinds of places. And I hope that this plants just a little bit of a seed in you and gets you thinking just a little bit differently about the kind of software that you can make either for yourself or for your community or at work or anywhere else. So that's really all I have for you. There's an incredible amount of detail and we can get into how any of this stuff works, but I figured I would cut it here and find out which parts you'd like to hear more about. All of the things I've talked about except upwelling are extremely thoroughly described at our website, inkanSwitch.com. A good entry point is our local first essay, which is a little older now, so the new work's not in it, but it covers a lot of these ideas in more depth. And then if you're interested in trying AutoMerge, I basically did the tutorial in 5 minutes. There's a little tutorial in the automerge.org website that you can try this as well. And we have lots of open source code up on the AutoMerge GitHub org and at InkanSwitch as well. And I happen to have some stickers that Martin Kleppmann made of the AutoMerge logo. If that's something that you're into, you can come and ask me, I'll give you one. All right, that's it.
Thank you, Peter. We have questions.
That was great, absolutely great. Thanks. Did you deliberately choose or tweak the URL for the upwelling demo to say Vigilant Dijkstra?
Oh no, that's just Netlify's, we call them haiku names at Heroku. So that's their just name generator. Yeah. Yeah.
Thank you. Yes?
Hi, that was an amazing talk, and I'll probably be annoying you this afternoon.
Great.
I have a small question around the multiple CRDTs. I've never actually worked with them.
Mm-hmm.
I'm imagining you would do something like have a master CRDT and add new CRDTs there, or?
Yeah, so the Pushpin paper talks about this in more depth. There's a lot of different ways that you can do this, and it's not clear that any one is the definitive way. It's worth noting that one of the things that is kind of exciting but can be a little intimidating about working in this space is that you can't just go look up on Stack Overflow what the best practices for things are. So you just got to kind of try stuff. But based on my experience, I would say that for me, anything that I would want to share independently, potentially, is kind of a good boundary for where to draw the bounds of a CRDT. So I would put a whole document into a CRDT if I wanted to be able to share that document. I wouldn't put 10 documents in unless somehow I would want to share them all together or copy them as one file. So if you imagine what you'd put in one file or share with one URL, to me that's kind of an intuitive argument for where I would put it. But I also have a friend who's working on a project where he's like, no, I just want to put it all in one big CRDT and that's my personal wiki and I'll just share it across my own devices and I don't want to think about anything else. It seems to be working for him. So yeah, that's what I would suggest.
Hello, impressive talk. I really like it. I was curious, how did you do or did you approach peer-to-peer discovery in Cambria project, for instance? That is
So
working-
Cambria is built on the Pushpin code base, our prototypes. Pushpin uses Hypercore and Hyperdiscovery, which are projects by Matthias Puss, and I think they call themselves the Hyper Team now. And that uses a distributed hash table to look up the public keys of the underlying documents. My implementation was kind of not scalable, and we're working on new approaches there. But when that works, it's like such an amazing feeling. So, it's worth looking at. Part of actually one of the really big problems there is that stuff doesn't work in the browser because it needs to communicate with the DHT over like TCP sockets, which you can't do in a browser today. You could with Chrome apps, but that is a whole other tale of sadness. So if you're going to go down that road, you're going to be in Electron land, and that's fine. But just as a warning, that's kind of what you should expect. But it's very cool when it works.
Oh, we have two questions. First, second.
Hi, thank you for the presentation. It was really amazing. I actually have a question about the company. So obviously you do great work in this like really niche field of research. I actually have a question like, how do you fund all these cool things that you do?
Yeah, we get this question a lot. The short answer is, and actually I can show you a little plug here. We're not affiliated with Actual. Actual is another great example of real production local first software that's built on these ideas. And the author, James Long, is a great engineer and has built his own CRDTs over SQLite. But Muse is actually a spin-out from the lab. So we're commercializing some of our other research work with Muse. And so this is kind of our model is we incubate work within the lab, and then when something is sufficiently developed to actually pursue it in the field, we try and spin out a company to pursue it.
Cool, thank you.
And we had a question here.
Hello. I've been following Automer's development for a little bit, and I read that you ran into issues when the documents were way big and you had a lot of changes.
Yeah.
So how that is going on, and
I have
what
exciting
are
news.
the limits about these big documents?
Yeah, so for the last year, Orion Henry, who's one of our lab members, has been working with the rest of the AutoMerge community on a new AutoMerge in Rust. It's AutoMerge-RS, and he just landed like 9 months of work, and it's like a 10,000x, okay, no, I don't think it's 300x speed up, and huge improvements in memory use. So the new AutoMerge WASM implementation, part of why we did this is we also wanted to be able to use AutoMerge on iOS and Android in a more native way. So now with this code base, we'll have native OS level performance and cross-platform support, and we're hoping to make that the default implementation at some point in the not too distant future. So I showed the JavaScript implementation today because I didn't want to run the risk of doing 2 demos at once. But the WASM implementation has had a huge step forward recently, and we're building all our new projects on top of that, including Upwelling, which I did show.
Okay, in this case, thank you very much.
Did anyone submit on the website? Oh, you had just told people to submit via the QR.
Yes.
Okay, that's good. Yeah. All right.
Can you check
Cool.
it as well? No?
All right.
Okay, great. Maybe you want to add something else?
No, thank you all for having me. It's good to see you.
Thank you very much.